Everyone. Good afternoon, everyone. Welcome to today's MTV Summer School lecture. My name is Shaun Clarke. I am a research scientist at the University of Michigan and the associate director for the MTV, and I will be doing today's lecture and also tomorrow's lecture. So it's going to be a two-part lecture on introduction to Monte Carlo. So if you have any questions, please feel free to put them into the chat. I see a bunch of folks typing their names into the chat. We don't need to take attendance in that way. As long as your name, your Zoom name is your full name, we can do it that way. So yeah, no need to do that. So without any further ado, I think we will go ahead and get started. Okay, great. So this week is all about Monte Carlo, which is a transport method that's commonly used in nuclear engineering applications. I'm going to give an overview. Today is mostly going to be background, a little bit of history on what the method is, and I want to go through some examples of how we can do random sampling, talk about random numbers, and that sort of thing. And then tomorrow, I'll go into some more of the details about some of the techniques that we can use to perform actual radiation transport problems using the Monte Carlo method. So first and foremost, what is the Monte Carlo method? It takes its origins in the Manhattan Project. So back in the mid 1940s, there were scientists that were interested in performing numerical simulations to help in design of the weapons they were working on in that time. So there were some discussions happening at Los Alamos National Lab, and there was a supercomputer there. This ENIAC acronym you see over here is the supercomputer of the time. And these three guys you see here at the bottom of the slide, Stan Ulam, Nick Metropolis, and John von Neumann, are largely considered to be the fathers of the Monte Carlo method, and they each sort of played a role in getting it started. So Stan Ulam was the first one to suggest using this computer to perform a method of statistical trials, while Nick Metropolis came up with the name Monte Carlo, which is kind of named after a famous city that's known for its gambling nightlife. And John von Neumann is the one that developed the first Monte Carlo computer code. So here we are, 60, 70, almost 80 years later, and the method is still going strong. It's still one of the main computer codes. MCNP is still maintained out of Los Alamos National Lab. In fact, maybe some of you are familiar with that code. We're not going to talk about how to use that or any specifics about that code, but it is one of the most common codes that get used to perform Monte Carlo calculations in nuclear engineering. So what is the Monte Carlo method? It's often kind of the term is thrown around by scientists and engineers, and it's not actually very easy to come up with an accurate and concise definition. In fact, I have a quote here on the slide explaining just that. It's difficult to construct the definition that characterizes Monte Carlo accurately, completely, and concisely. But basically, it involves some sort of random sampling. That's kind of the heart of a Monte Carlo calculation. It's going to be some sort of process that involves random sampling, and we'll get into what we mean by that later on in the lecture. So here's a survey of some definitions. I just grabbed several popular textbooks. Apologies, I don't have the full references here, but if you just type the author's name here that's underlined in Monte Carlo, I'm sure you can find many of these references online. They're very common. And if you take a look at them, and I'm not going to read them all to you, but if you just survey them visually, you can see several common themes in these definitions. And basically, you see the word random popping up a lot. Random variables, random sampling, statistical simulation, probability. Those are all the main ideas that we think of when we talk about Monte Carlo modeling or Monte Carlo sampling. So the definitions include random sampling, pseudo-random numbers, things like that. So what are pseudo-random numbers? Random numbers are truly random. Pseudo-random are not truly random, but they have a number of key properties that allow us to perform Monte Carlo calculations in a quick and efficient manner. So the definition here at the bottom is what a pseudo-random number is: a sequence of positive real numbers. They're usually denoted by the Greek letter xi, and they're distributed uniformly on the interval between 0 and 1. So the key part of this definition of pseudo-random numbers is this kind of the word sequence. So if random numbers are truly random, there's no way to predict based on one random number what the next random number will be, because it's random. But that's not really efficient in a computer calculation. So to perform Monte Carlo calculations in large computer codes, we use pseudo-random numbers, which are sequenced and able to be produced by the computer. So these random numbers get used to statistically sample the physical quantities that we're interested in. So maybe we're looking at neutron energy, or gamma ray scattering angle, these types of things. We use random numbers to essentially reproduce these quantities from the known physical distributions. If we do a large number of trials, we can obtain reliable statistical approximations of those distributions. So the third bullet here is essentially the central limit theorem. So if we're performing a large number of trials or a large number of samples from a certain distribution, our set will converge eventually to that distribution. And that convergence is statistically known, and we can mathematically express the uncertainty in our distribution as a function of the number of scores. In fact, here at the bottom, statistical uncertainty is estimated by the inverse square root of the number of scores. So if we have a large number of scores for whatever distribution we're trying to score, the uncertainty or statistical uncertainty in that distribution will be small. So again, how do we actually apply the Monte Carlo method? Well, the first thing we need are a set of random numbers, and the second thing we need are distributions. So let's talk a little bit about the random numbers. Again, these pseudo-random numbers are generated on the interval 0, 1, and they're generated on a computer using a mathematical algorithm. So that's the important distinction between pseudo-random numbers and truly random numbers, is that we are producing these on a computer using essentially what's known as a recursive relationship. So every random number that the code generates is dependent upon the previous random number, which means they're not truly random. But there are a number of statistical tests that one can apply to ensure that the random numbers that are being produced are sufficiently random. I'm not going to go into what sufficiently random means, but suffice to say, there's a few properties here that we need to think about. Firstly, of course, the interval we talked about, but the second one here, they need to be produced speedily. What does speedily mean? Essentially, when you're running a Monte Carlo calculation, if you're doing a typical neutron transport or nuclear engineering problem, you're going to need a lot of random numbers. By a lot, I mean you can use 10 to the 10 to the 10, 10 to the 12, 10 to the 14. Very large numbers of random numbers are needed to perform complex calculations. So it's important that the computer can produce these without adding extra expense onto our calculation, because we're going to need to do this random numbers calculation many times. The third bullet here, reproducible. That's a little bit of an odd one. So why do we want our pseudo-random numbers to be reproducible? This has to do with code verification and reproduction of the solution. So if I'm running a calculation using random numbers and one of my colleagues is running the calculation, it'd be nice if we can get the same answer so that we know if the codes are working. So because random number. If the random numbers were truly random, there'd be no way to know if we were getting a different answer because of the randomness of our generator or because the code was actually doing something that we didn't want it to. So reproducibility helps with things like debugging, code verification. The final bullet there, have a long cycle length. What does this mean? So these generators, because they're recursive relationships, every number depends on the previous number. Eventually, they actually start over. So if you make enough random numbers using this relationship, eventually you're going to get back the random number that you start with. And that number, how many random numbers you can sample before the cycle resets, is called the cycle length. So the cycle length, or the cycles of random number generators that are used in commercial Monte Carlo codes, are typically on the order of 10 to the 18. Some can be longer, some can be shorter, but 10 to the 18 is kind of a typical cycle length. You can look in, if you use Python or MATLAB, even Excel has a random number generator built into it. If you just type the word rand, I think it works in Excel or MATLAB, and it'll make random numbers, and you can look at that up in the manual, and it'll tell you the cycle length. It'll tell you which algorithm that it uses. I've listed a few algorithms here at the bottom. Essentially, these are just the way that they define the recursive relationship that's used in those codes, and you can look them up, and then they're all sufficiently random, but they will have different cycle lengths depending on the type of application that they're being used for. So all of this is typically handled under the hood. If you're grabbing a commercial Monte Carlo code like MCMP or Scale, any of these other Monte Carlo codes that you can get your hands on, these random number generators are going to be built into the code. All the details are going to be handled under the hood. But if you're making your own Monte Carlo algorithm to solve something else in your research, or some other application, maybe you're using the one in MATLAB or the one in Python, it's important to look up the cycle lengths and the properties of that generator, so that that the numbers that you're using are going to be sufficiently random. Yeah, speaking of sufficiently random, this is a comic strip that I pulled. It's pretty old at this point, but it's this idea that if the random numbers are truly random, there's no way to tell if it's actually random. So this guy's making random numbers, 99999. So that the probability of getting any one number is just the same if it's random. So 9999 would be the same as probability of computing any other set of 6 numbers. So that's the idea. Randomness. Okay. So what do we do with these random numbers? How do we actually use them to sample the quantity of interest? We do this using something called random sampling. And the heart of the random sampling process is something known as the probability density function. P of X is typically how you'll see it written in various textbooks. So this P of X is the distribution, or that describes the probability of some behavior of the variable X. So maybe we're looking at an energy distribution, or an angular distribution, or a spatial distribution. That distribution, that behavior, is physically described by this function, P of X. In order to be a PDF, P of X needs to satisfy 2 main properties. The first property is that it has to be normalized over the entire problem domain. So whatever X is, if it's distance or time or energy, whatever, if that's integrated over all space for that variable, it must integrate to 1, which basically means something has to happen. It's a probability. So it must be normalized over the entire problem domain. The second probability is that it has to be positive. So it's a probability. So once we have this small P of X, we can use that and create a cumulative density function, or a CDF. And the CDF is commonly kind of shown in textbooks as this capital P of X. And this capital P of X, the CDF, is a cumulative integral of the PDF. So if you can write capital P of X as the integral from 0, this can be negative infinity, depending on if it's time or whatever, but from the lower bound of your space, of your problem space, up to X, P of X prime. So this capital P of X is a function of X. It's a cumulative integral of the PDF. And then once we have the CDF, the cumulative density function, this CDF is what we use to perform the random sampling. So if we have our CDF, capital P of x, defined as, again, the integral of 0 to x, P of x prime dx prime, we can take that CDF and set it equal to our random number C. And by doing this, because again, the CDF, because it's a cumulative integral, it's going to go from 0 to 1. Our random number also is on the interval of 0 to 1. So by equating these two and solving for x, we can express x as a function of our random number C. So this mathematical process of taking in the CDF, setting it equal to random number, solving for x, this is a process known as random sampling. Technically, this is the inverse transform approach, where we have a P of x that's a nice mathematical function that can be solved easily. And we can do this integral, we can write it out, it's an analytic solution. If you can do that, you can express your parameter x as a function of a random number. And then by sampling a random number, choosing one at random, that then corresponds back to a variable x. And again, that process is called random sampling. I know it's a bit esoteric, so I'm going to show a few examples here that will hopefully make it a little more clear. Okay, so I'm going to go through 3 examples here, 3 or 4 if we have time. No, it's already 1:20. So I'm going to talk a little bit about a dice throw, because that's an easy example that I think we can all understand. And then I'm going to talk about a hit or miss experiment and the Buffon's needle experiment. These are kind of classical Monte Carlo examples that you can find in pretty much any textbook. And then depending on how much time we have, we'll start talking about transport today, and that'll kind of lead us into the rest of the lecture tomorrow. So we're going to consider, for the first example, the throwing of a single die. We're going to talk about a die here that's got 6 sides. So a standard 6-sided die where each side is equally probable. And this is typically called a fair 6-sided die. And we want to do an experiment where we want to calculate the average outcome of a single roll of this 6-sided die. So we can do this experimentally. We could get a die or a set of dice and we could roll them however many times we wanted, some number, big N. We could record the outcomes of these big N rolls in this vector C. And once we had our set of outcomes in this vector C, we could just take the average, take the mathematical average by just adding up all the outcomes and dividing by the number of throws. So if you were to do this experimentally, and if you performed enough trials, meaning if big N was large enough, you would calculate this average experimentally to be 3.5. If you did it with just one roll, you may or may not get the proper outcome. So if you just roll a single die and the result of the roll is 4, that's going to imply the average is 4, which isn't true. It's 3.5. So this kind of illustrates that you need to roll many dice to accurately calculate the average, even for something as simple as rolling a die. Similar argument of flipping a coin. Heads or tails should be equally probable, but if you flip it 2 or 3 times, you can get three heads in a row or 3 tails in a row. So thinking about it in this way sort of illustrates the idea of why we need a large number of statistical trials. And that large number, meaning that if this vector C is long enough, we would expect to see equal outcomes of 1, 2, 3, 4, 5, and 6. If you do that, we can give you the average to be 3.5. So what if we don't want to do this experimentally? What if we want to use a Monte Carlo calculation to actually do this on a computer rather than physically rolling these dice, for this many times? So we can do that. We can simulate a single die throw using a Monte Carlo calculation. So our our task here would be to simulate n throws. So we want to do it in a large number of times. We'll do it by simulating n random numbers. So like any Monte Carlo calculation, if we want to do our random sampling, the first thing we need is a PDF. So in this case, because it's a regular or a fair six-sided die, it's actually a discrete PDF. I didn't want to talk about this, but it's discrete because the outcomes are either 1 or 2 or 3 or 4 or 5 or 6. So it's a discrete PDF where the probability of any single outcome is 1/6, because we're assuming this is a fair six-sided die. So our PDF, lowercase PDF, is simply just 1/6 dx. So it's a constant probability for any single outcome. In order to do the random sampling, the PDF needs to be transformed into a CDF. So again, the CDF is a cumulative integral of the PDF, lowercase PDF. It can be written this way, where it's essentially a running sum. So P1 is 1/6, P2 is also 1/6 because it's a fair six-sided die. So big P sub I is the probability that we'll obtain any outcome less than or equal to I. Okay, in this case, because it's discrete, it's actually makes a lot more sense to me to look at it visually. So this is a visualization of what the CDF would look like for rolling a single fair six-sided die. So the probability of any one outcome is 1/6, so or 0.1667 if you were to write it as a decimal, and that's our P1, lowercase p1 and uppercase P1, PDF and CDF. The CDF is a running integral, so this is actually a typo. This should be P2, is P1 plus P2, which is a third, which is the probability of getting the outcome of 2 or 1. P3 is P1 plus P2 plus P3, which is half, which is the probability of getting any outcome 3, 2, or 1, so on and so forth. So if we build the CDF in this way, then we can use our random sampling to actually sample the outcome of a single die roll. Okay, so the y-axis here goes from 0 to 1, so we would sample a random number from our random number generator, and it would spit out a value between 0 and 1. So say it spits out, I don't know, 0.4. If it spits out 0.4, we land here. That would correspond to an outcome of 3 on the dice roll. If we sample another random number and it spits out 0.7, that's going to land up here in this band. 0.7 lands in this band. That would correspond to an outcome of 5 on the six-sided die. Okay. If we did another one, maybe it spits out 0.9, which falls in this band up here. That would correspond to an outcome of 6. Okay, so you could write a script to do this where you're using whatever random number generator exists in MATLAB or Python or whatever scripting language you have access to. You would sample a random number on this interval and check which of these bands it falls into, and that band corresponds to the outcome of the die roll. And you could do this however many times you wanted to roll the dice by just sampling these numbers, and that would provide a Monte Carlo analog to the physical experiment of rolling those dice. Okay, I want to pause real quick and just ask if there are any questions before I go to the next example. Okay, great. This slide just is showing that we can compute the average in the same way, so we don't need to dwell on that. So the next example that I want to talk about is something called a hit or miss experiment or Monte Carlo integral. And the thought problem here is how to compute the area of an arbitrary and complex plane S. So we got a little drawing here. We've got this surface S, and we want to compute the area of that surface, and we're assuming that the surface is complex enough that you can't just perform a numerical integral. It's a completely arbitrary and complex surface. So we can do a thought experiment that involves the surface S, and maybe it's bounded in this square that's AB, CD completely bounds our surface S. Okay, if we had that situation, if we had a physical surface, what we could do is we could imagine somebody throwing darts or arrows at this region of the blue square here, and some number of those arrows would hit the plane S, and some would miss. Some would land in the blue region, some would land in the green region. And if we did enough of those trials, if we threw enough arrows, we could estimate the area of S given the number of arrows that actually hit it. And you can do that by just taking the ratio. So lowercase n would be the number of arrows that hit the surface S. Big N would be the number of arrows that were thrown in total, times the area of the rectangle, which is easily computable, B minus A times D minus C. That ratio times the area of the rectangle would produce the surface area A, the area of surface S A. So that's a kind of an arduous thing to do in real life, throwing darts and arrows, but we can have the same situation in a Monte Carlo calculation where we can simulate or we can sample the coordinates of these dart throws in this rectangle here, and that would allow us to approximate this area. So to do this, we need pairs of random numbers. So if we're trying to throw or simulate n arrow throws on this surface, we need n pairs of random numbers. So in this case, it's not one number we need, it's two, because we're trying to simulate a coordinate x, y. You can also think about this in a 3D application, but it's easier to visualize on a 2D space. So we need n pairs of random numbers, and each pair will correspond to a point inside the rectangle that is labeled here x, y. So to do this, if we again assume that our plane is distributed between B and A on the x-axis and between D and C on the y-axis, we can sample our x coordinate using our first random number, xi, as A, the lower bound, plus B minus A times a random number. Remember, this xi, the random numbers, are distributed between 0 and 1. So if we get 0 for xi, excuse me, we get B. If we get 1 for psi, we get A. And the same thing for the y value. We need another random number called eta in this case. Same idea here. If eta is distributed on 0, 1, the variable y is going to be distributed between D and C. And we can repeat this a large number of times, and that will produce an estimate of the surface area of S. And we can do this estimate in the same exact way that you would do it experimentally. So we take a ratio of the number of trials, or the number of times that xy lands inside the surface, and we know how many trials we performed, in this case k, and that ratio will tell us, when multiplied by the area of the rectangle, will tell us will tell us the area of the surface area S. We could also compute standard deviation of that if we wanted to, using the formula here at the bottom. So just to revisit the archer metaphor. So in this case, if the archer is skilled, meaning that if he or she is trying to hit the surface S, that's going to mess up our estimate, right? So we need to assume that all of these points are uniformly distributed on our plane. Okay, and that's really the fundamental assumption of this approach. You can imagine if someone's trying to hit the surface, then the number that hit it is going to be unfairly biased high, which is not going to give us a true estimate of the area. So this is kind of the visual way to think about why random numbers need to be uniformly distributed. It's the same thing with if you're doing a radiation transport calculation, same thing. You need these numbers to be uniformly distributed so that the solution is not biased. The last one here that's important is X and Y need to be independent variables. So if you're just throwing an arrow at random at this board, there's no reason that the Y coordinate would be dependent on the X coordinate unless again you were trying to aim in a certain area. So X and Y need to be completely independent. So in this case, if you're using a random number generator, you would sample one random number after the other, and those would be the two numbers that you would use to get the X and Y coordinates. Of course, because they're pseudo-random numbers, they technically depend on one another, but because the assumption is that the pseudo-random number generator is sufficiently random, it's safe to treat X and Y as independent variables. Okay, the last one here is an experiment called the Buffon's needle problem. If you've not heard of this, you can Google it. It's like a well-known thought experiment that involves Monte Carlo. I'm just going to walk through that briefly here. The problem is set up like this. So there's a needle. You can think of needles that are a constant length, so length L, and they're randomly thrown onto a horizontal plane with parallel straight lines. So you can imagine like a hardwood floor or some type of floor that has planks. So the question is, the question that this French mathematician Buffon was considering is, if I was to randomly drop a large number of these needles on my floor, what's the probability that one of them will intersect one of the planes on one of the slats on his floor? So you can see it visually here. All these needles, some of them intersect the lines, some of them don't. So the question is, what's the probability that will or will not occur? So in this case, the needle we're going to consider to be length L, and the spacing between the lines on the floor we're going to consider to be length D. And every time that a needle is dropped on the floor, it's gonna, if you drop a parallel line to the closest slat, we'll call that X, and then the angle that the needle makes with the floor, we're going to call that theta. And there's essentially two conditions. There's the needle does or does not intersect the line. And we can think about it in this way. So if the needle does intersect the line, that is the situation in which X, this perpendicular, is less than L over 2 sine theta. And if it does not intersect, we have the condition here on the right where L over 2 sine theta is less than X. So we can think about this visually of all the possible coordinates. So our theta can be anything between 0 and pi, and our X coordinate can be anything between 0 and 2. And we can actually think of this in a similar way to the hit or miss problem that we just talked about. And we can look at our L over 2 sine theta function as the set of coordinates. So remember on the previous page, X less than L over 2 sine theta, that was the set of positions, X theta, where the needle intersected one of the lines. Okay, so we can do that integral, and you can solve that integral easily enough to be 2L over pi d, and that's the probability that any needle will intersect the line. And the interesting thing about this is you can use this expression if you had a way to actually physically measure this probability p, because if we could measure this, we could actually estimate pi. That's what I'm trying to say. So if you know L, then the length of the needle, and you know the spacing between the lines on the floor, if you were to do this experiment physically, dropping needles on the floor, you could actually solve this for pi. Okay, so pi would equal 2L over P D. Actually, go a slide on it. Yeah, pi would be 2L over PD. So you know L, you know D. you can measure P. If you can measure P, you can measure pi. So this was kind of the thought experiment that was done, and it actually gives a way to compute or estimate pi using Monte Carlo methods. So how do we measure P? Well, we can, if we drop some number of needles n onto the floor, if m out of those n hit or intersect the lines, then we can compute pi as 2 ln over md. And I think the question in the chat was just getting to this last point here, which is what is the quality of the estimate? I'm not gonna go to this link because I don't want to spend the time on that. But if you just Google Buffon's needle, there are several little apps online that'll show you and let you type in, the number of needles you want to drop. But I think I have a little table on the next slide that show you that. So here's a few examples through the years, through the different centuries and decades of people that have done this in the past, and you can see the numbers here, thousands of needles getting dropped, and how well those trials actually estimate pi. And you can see it's not always related to the number in general. The higher numbers don't have a better estimate of pi in this case. This is an experiment, so it's not ideal. But you can see it is a pretty good job. So if you have some free time this evening and you want to drop 3,000 to 5,000 needles on your floor and count them all, you can estimate pi to pretty good precision. Actually, this is 3.14159. This is 7 digits of precision estimated pi in the year 1901 using this approach. So yeah, I will talk more about this question. How can we know how many trials are enough to provide statistical rules? Probably more so tomorrow than I will today. But to give you a short answer today is there is no way a priori to know how many trials are enough. It depends on the problem. It depends on the PDF and the CDFs that you're sampling in the Monte Carlo problem, how many trials you need. If it's a simple PDF or simple CDF, you can get away with a few number of trials. If it's a complex PDF, you will need more trials. Okay, so there's no way to know a priori. You could think of it as flipping a coin. The probability is 50-50. There's only 2 outcomes. So you wouldn't need to flip it too many times to estimate that probability as 50%. But if you're trying to estimate pi, for example, we need many, many more trials. So it depends on the complexity of your PDF. Yeah. Thank you for the question. And then let's just talk briefly about this last one. I think we'll then stop there for the day. Oops, here we go. So I want to talk a little bit about something that's more relevant to nuclear engineering here as we wrap up for the day. And we're going to talk about penetration through shielding material. So we're going to think about a block of shield and how likely is it that some particle, neutron or gamma, can actually transmit through that block. That's something we can easily compute analytically, but we can also compute it using Monte Carlo. And in fact, in this case, if we think about it in a really simple way, we can actually solve this Monte Carlo problem using a set of 6-sided dice. So we're going to consider this situation where we have a slab of material that's call them half layers, so 4 half layers thick, meaning that each of these pieces is thick enough that half of the incident radiation is stopped. Or in other words, every particle that enters that slab has a 50% chance of transmitting through the other side of that slab. So if there's 4 consecutive slabs, we can easily compute the total transmission probability as 1/2 times 1/2 times 1/2 times 1/2, or 1/16, or 6.25% is our transmission probability. And that's essentially the number that make it through, lowercase n, divided by the number that start, n0. So that's easy enough to compute analytically. We could also compute it using Monte Carlo And furthermore, we could actually compute it using dice. I sometimes do this in a live classroom of students where we pass out dice and we actually do this calculation live in the classroom. Unfortunately, we're on Zoom, so we're not going to be able to do that. So we're just going to treat it like a thought experiment here. So if we know that the transmission probability through every half layer is 50%, we can use the dice as our random number generator. So we can define it, say, okay, we're going to throw the dice to make our random numbers, and any rolls of 1, 2, and 3, we're going to treat that as the particle being absorbed, and any rolls of 4, 5, 6, we'll treat those as the particle being transmitted. So if we were in a real classroom, I would have everybody stand up, and then you would all roll the dice, and any student that rolled a 1, 2, or 3 would be seated. The rest would remain standing. 4, 5, and 6 are transmitted, and then we would do it again and again and again. And after the four slabs, there would be a certain number of students standing. So in this case, we have 83 people in the room. So you would expect 1/16 of that to be standing at the end of this. And based on the number of students in the room, you can get a pretty good estimate of this probability using a simple random number generator that is a simple fair 6-sided die. Furthermore, we could estimate the uncertainty on our solutions. So if we did this problem in real life and we got to the end and there were, say, 2 students standing, then our outcome would be 2 over 83. And we could say, okay, well, the uncertainty in that is 1 over the square root of the number of scores. So 1 over root 2, which would be like 70% uncertainty, which is not good. And we would be able to kind of really visualize that, for a low number of scores, the result, statistically speaking, is not reliable. For a Monte Carlo calculation, you need a large number of scores to produce a statistically reliable result. Okay, and then there are other approaches we can take to do this calculation in a more statistically reliable way. We can do things like particle splitting. This is getting a little bit into the details, but what we can do is we can actually artificially increase the population of the particles in each slab to increase our overall number of scores. So consider a case where after a particle is transmitted through each half layer, we then take that particle and split it into 2 more particles. Okay, so artificially increasing the number of particles in each slab by a factor of 2. To do that, to compensate for that, we would actually take the weight of the particle. So the weight is how much a particle contributes to a certain tally score. So we would take the weight of that particle and reduce it by the splitting fraction. So if we're splitting every particle into 2 particles, the weight of those particles would then be 1/2 of whatever it used to be. So we're increasing the population, but each particle that scores is contributing less to the overall tally result. So if you run the numbers, the tally estimate at the end, instead of being just the number that make it through over the number that started, it is that ratio, but corrected by the number of splits. So if we're going to split everything by 2, which is what we set up here, split into 2 particles, W would be 1/2, and we're going to split M times. So M is the number of times that it gets split. This comes as a correction factor to the overall tally ratio, and the actual score is preserved. So if we're splitting everything by 2 3 times, this N would be a factor of 8 too large because we've increased all the particles by the splitting, but then we would correct that by dividing by 8 at the end, which is 1/2 to the 3rd power. So this is just a way to visualize how particle splitting works in Monte Carlo. It's something that gets done very commonly in application, and we'll talk about this more tomorrow because we're going to talk about how to estimate flux and things like that using Monte Carlo, and we'll revisit this concept of weight and particle splitting and tally contributions and all of these things tomorrow. So yeah, maybe we'll just leave it there and talk about it more tomorrow if there's questions. So the last thing I just want to touch on here in the last minutes is why use the Monte Carlo method? Why is it apply? What are some advantages, some disadvantages? So the advantages are it's essentially a numerical analog to a physical experiment. So whatever complexity exists in your physical experiment, as long as you have probability distributions for those behavior, you can model them directly in the Monte Carlo calculation. It's capable of representing the complex geometries, so there's no homogenization required that are needed in other approaches. Discrete approaches often use homogenization both in space and or energy, which creates approximations. So if you think about energy grouping or energy homogenization, Monte Carlo is typically using point-wise numerical data. So there's none of these approximations are needed. The other advantage is it's often used as numerical result to validate other deterministic methods. So because it typically involves so few assumptions compared to deterministic approaches, the Monte Carlo can often be treated as a numerical benchmark in those cases. So what are the disadvantages? It can use a lot of memory. So depending on the size of your problem and how much data you're loading in, because Monte Carlo typically uses point-wise cross-section data, all that data has to be loaded into the memory to do the calculation. So you can end up, if the problem is complex, you can end up requiring many tens of gigs of RAM to do calculation. Now with computers nowadays, that's less of an issue, but it's still an issue. The second point here, long run times, is essentially related to the fact that the quality of your estimate depends on the number of scores. So if you want an estimate with very high precision, you need a very long or very large number of scores. So that can, because you need the large number of scores, that can relate or result in long runtimes. Long is relative and it depends on your machine. I should also mention that the Monte Carlo method, because the fundamental assumption of Monte Carlo is a large number of independent statistical trials. So the method lends itself very well to parallel computing. So you can farm out many of these processes, these independent processes, on independent processors, and then bring the solution back together at the end. So while it can require long runtimes, it's also very amicable to parallel computing. Okay, so with that is the end of what I wanted to cover today. We have 5 minutes left. Let's see, there's a question in the chat. Is the high precision of Monte Carlo synonymous with confidence intervals? Yes. Yes. So I think what you're getting at is because of the statistical convergence of Monte Carlo, we can use that to set confidence intervals on our solution. So if we can say 1 sigma, 2 sigma, we can use those variances to set up confidence bands for our solution in Monte Carlo. Are there any other questions for today? Relative uncertainty goes as 1 over root n, can be understood as, yes, kind of. So it's so the question, I guess you can all see the chat, but the student is asking if we can understand this disproportionality of the uncertainty to 1 over root n as some constant over root n. That's not entirely true. So the reason we don't say it is 1 over root n is because that's for, if you look at the manual for some of these codes, it'll say that the uncertainty scales is 1 over root n for a well-behaved tally. So it basically means it goes as 1 over root n if n is large enough. So if n is 1 or 2 or 3, it's not going to scale. So once the problem begins to converge, at that point, it'll then scale as 1 over root n. Other questions? Okay, perfect. Well, again, I'm going to be with you all again tomorrow. So if you have any questions that you think of later, you can hold them. and bring them tomorrow, and we can address them at that point, and maybe I'll even answer some of them during tomorrow's lecture as well. So with that, I'll thank you all for your attention, and look forward to seeing you again tomorrow.